Welcome back. In this part of lesson 5, we're going to talk about the general equation for a line as a vector-valued function in R2. To define a line in R2 as a vector-valued function, we need two things. A direction vector, which we'll call v, and we'll say that v has the direction a comma b. We go a units over and b units up. In addition to a direction vector, we also need a point on the line. And we'll call that point r naught, and we'll say that it is given by x naught, y naught, which are just individual values. And you can think about these from the scalar world as a slope. That's what we call the slope, and a point on the line. Then we say that the vector equation for a line is given by r of t, a vector valued output, which has two components, x of t, y of t. And these two components come from scalar vector multiplication and vector-vector addition. Here we have vector-vector addition. Here we have scalar vector multiplication. We can use the component definitions of r naught and v to find specific representations of x of t and y of t in terms of scalars. R naught was x naught, y naught. Here we have t times ab. We can bring in the t and then add individually. So this is a times t, of course. And then here we have y plus b times t. And this immediately implies that x of t is equal to x naught plus at, and then y of t is equal to y naught plus bt. And these are the parametric equations for x and y. One thing that you'll notice is we can actually translate this back into scalar form. To do so, we recognize that the direction vector encodes a slope. If we go a units to the right and b units up or down, then the slope would be b divided by a, which implies that the point slope form of the line would be y minus y naught times m, which we just said was b over a, outside of x minus x naught, which is really exciting because this allows us to go from the vector description to the scalar description. Let's take a look at an example of how we might use this in practice to define a line. In this example, we're going to define a vector equation for a line that moves in the direction 3, 4 and through the point -2, 2. In order to do this, we do a quick recall. Remember that an equation for a line in R2 is given as a vector as r naught, a point on the line, written as a vector, plus t times the direction. Here we've got this as -2, 2, because we're given that in the problem statement. And then we've got the parameter t times the direction 3, 4. This direction represents moving 3 units to the right and 4 units upwards. When we combine these together, we have -2 plus 3t in the x component, and the y component would be +2 plus 4t, which we said if we wrote as a parametric equation would be x of t and y of t. And just for giggles, we might as well write those out specifically so that we have all the clarity in the world about what each component is given by. Now that we have this part specified, let's go into Mathematica and start graphing this parametric equation. Because it's in R2, we will use parametric plot. If it was in R3, we would use parametric plot 3D, which we'll be doing in future videos. Let's switch over to Mathematica. Here we are in Mathematica. We're going to begin by defining our vector direction for our line, which we said was 3, 4. And then we're also going to go ahead and define R naught. To get the little subscript there, I just push Control _. And R naught was given, in this case, -2, 2. I suppress both of those outputs because I don't need it. The vector equation for the line, we were going to have two functions. We were going to have x of t and y of t. And remember, we wanted to graph this with parametric plot. Open bracket, close bracket. I like to comment my code so that I understand what I'm doing. So here I'm going to say, please end the parametric plot command. The first entry of parametric plot is going to be the individual component. So remember that the x of t was -2 plus 3t. Y of t was going to be 2 plus 4t. And then we need to tell Mathematica what values of t we would like. Let's, for fun, go from t equals 0 to 1. So we've just specified that the t range, the parameter range, will start at 0 and go to 1. And let's evaluate this. So I hold shift and push enter on my keyboard. There is the evaluation. It's a little bit small. Let's zoom, a little bit big. Let's zoom out a little bit so I can see the command and the plot together. Here, you'll notice that the output value is a single vector. If I control the plot range by telling Mathematica the exact plot range that I want, and we're going to do this with an external bracket to represent the entirety of the plot range, and then we have two internal brackets. The internal brackets are going to tell me the x and the y values, so I'm going to let x range from -4 to 4, and perhaps we let y range from -4 to +4, just to see what happens. I know that's not going to be enough because my y gains are going to be bigger than my x gains. So maybe I go all the way up to +10 here. And what's really interesting about this graph, notice that it's a lined segment. The reason it's a line segment has to do with the parameters of t. If I let t go from lower bound -1, I should get a longer line segment. There it is. In this case, I will zoom out a little bit in Mathematica by changing the x range. All right. And then if we increase t from -1 to -2, I get an even longer line. And let's see what's happening here. To do so, I'm going to go ahead and use the show command, as we've done so often in Mathematica videos from the past. I end the show command. I'm going to go ahead and use a graphic. And the graphics I'm going to use is a point. So I use the internal bracket pair, and I do point size. Point size is going to be 0.01 perhaps. And then I'm going to graph the point. Let's graph R naught, just to see where that is. All right, let's increase the point size so you can see it a little bit. Okay, so there's the point R naught. And now I want to show what's going on with the direction vector v. So in order to do this, I'm going to copy and paste that command. But in this case, I'm going to call this an arrow. And I'd like the arrow to go from the origin to the vector v. And I haven't defined the origin yet. That's why Mathematica is complaining. So here the origin, lowercase o, is going to be 0, 0. Suppress that output. And then maybe we want to be a little bit exciting and call this red. Notice this vector v that we have here is starting at the origin. When we look at the line, the vector v as written, 3, 4, is not on that line. However, once we add the vector r, which is negative 2 times 2, and then we take scalar multiples of v, we end up with this entire line. And so you see that the direction of this vector v, the direction of the red vector, is actually parallel. It's in the same direction as the line that we create using this parametric plot. In the next video, we'll begin to look at vector-valued functions in R2 that are not lines, like circles. Ooh, are you ready?